Good afternoon, everyone. Good afternoon, and welcome, a very warm welcome on this very cold day to the Neil Armstrong Hall of Engineering. Welcome to all the guests here today, many distinguished guests, students, faculty, and staff who are here today. At the onset, I'd like to recognize three individuals who are actually going to be on the Purdue One flight, three to-be astronauts. So will Professor Collicott, Abby, and Jason, would you please stand so we might recognize you? Now, 4 months and 5 days ago, in this great hall, Purdue made a remarkable announcement that in partnership with Virgin Galactic, we would try something that has never been tried in the history of humankind. That we would try a suborbital space flight entirely crewed by people from one university, Purdue University. It's never been done before. The idea that the essential functions of a university, teaching, learning, education, alumni engagement, are not restricted by the surly bonds of gravity. They can happen, and they will happen in the depths of space as well. This mission is called Purdue One. Why? Well, because we expect many more of them in the future. This is a remarkable mission and is destined to break so many records. It already will accomplish 2 firsts. This will be the first time that a student and a faculty from the same university are up in space doing education and teaching and learning together and research. This will be the first time that crew entirely from one university are in space on a flight working together. And today, we add to that list of records 2 firsts, 2 new firsts. I'm proud to announce that we have selected 2 amazing projects, first-of-kind projects, for the remaining 2 experiment lockers on Purdue One. The first of those projects is the quantum navigation, positioning, and timekeeping technology system. This is a partnership between Purdue University and Inflection, a company that you'll hear from here shortly. And if successful, this experiment, which involves laser-cooled atoms using quantum mechanical phenomena for navigation, positioning, and timekeeping in space, could set the foundations of future in-space navigation that is far more accurate than GPS and does not require GPS. Think about that. That's absolutely remarkable. Will please join me in a round of applause for the Quantum PNT System project leaders and the team here for being selected on this flight. The second announcement is equally exciting. The second project that's been selected for the second experimental locker is the In-Space Semiconductor Manufacturing and Operations team. This team is going to be attempting an experiment, an autonomous experiment in space, using laser processing technology for microelectronics and advanced manufacturing in space. They are going to demonstrate that it's actually possible to fabricate, fix, repair, and validate advanced manufactured components in the depths of space. Would you please join me in a round of applause for the In-Space Semiconductor Manufacturing and Operations team as well. Without further ado, I'd like to invite Tendril Kamal, our senior in aeronautics and astronautics. And Tendril has been an amazing spokesperson for the Purdue One mission. And she's going to be the moderator for our 2 special panels that are going to follow to tell you much more about these 2 exciting projects. Tendril, thank you. Please join me on the stage and boiler up and hail Purdue, everyone.
Thank you, Dean Rahman. Good afternoon, students, faculty, alumni, and our guests from various diverse industries across the United States. My name is Thendril Kamal, and it is an honor to be your moderator for the research panels this afternoon. As a student, it's not every day that you witness history being made at your undergraduate institution. But Purdue has a way of reminding us that what sounds impossible can become a campus headline. Today, you'll be hearing from the teams and strategic partners behind 2 selected payloads flying on board Purdue One, projects that take ideas we usually only see in research papers and bring them into a real microgravity environment. As you listen tonight, I'm also hearing this as an aerospace engineering student who's learned that so much of engineering comes down to trust in structures, systems, in what you can validate. So I invite you all, especially my peers, to think about the future. Not just what this research proves in microgravity, but what it unlocks for future engineers like us, who will turn brand new physics into dependable flight hardware. With that being said, let's dive right into the first panel of the afternoon, focused on something that sounds like science fiction, but is quickly becoming a necessity: quantum positioning, navigation, and timing without GPS. We all use GPS every day. Phones, cars, aircraft. It's also surprisingly fragile. It can be jammed, spoofed, or blocked. So the question is, what happens when you're in deep space and GPS isn't an option? That's where this Purdue One experiment comes in. This team is designing a cold atom system using laser cold atoms as an ultra-precise clock and sensor to lay the foundation for quantum navigation in space. If that sounds straight out of an episode of Star Trek, just wait until you hear it from the experts themselves. Ladies and gentlemen, please join me in welcoming to the stage Professor Shengwang Du from Purdue Electrical and Computer Engineering and Deputy Director of the Purdue Quantum Science and Engineering Institute. Professor Sasha Boltaseva, Ron and Dottie Garvin Tonjes, Distinguished Professor of Electrical and Computer Engineering. And lastly, Dr. Dana Anderson, the founder and chief science officer at Inflection, a world leader in deployed quantum technology, including cold atom systems already tested in space environments like the ISS. Testing. Perfect. Awesome. Professor Du, let's get started with the big picture of this. So for someone hearing about this for the very first time, can you tell us exactly what you and your team intend to fly on Purdue One? What are the goals of your experiment?
So this project is about exploring a new kind of navigation technology we call quantum positioning, navigation, and timing, or QPNT. So unlike today's GPS system, so QPNT uses the laws of quantum physics to provide navigation and timing information that is far more precise than GPS. So in this Purdue One mission, our goal is to take the first step, very critical step towards that future. So we are going to use laser light to cool and trap rubidium atoms to a temperature close to absolute zero, just a few micron Kelvin. So at such ultra-cold temperature, we are going to characterize the quantum properties of those atoms. And this, we call this Pathfinder experiment, will lay down the scientific and engineering foundation for the future quantum navigation system that could one day guide satellites, spacecraft, and deeper space missions.
Pathfinder is such an apt name for the experiment. It really is going to be a trailblazer in quantum navigation systems. So let's talk about why it matters right now. Dr. Anderson, you've built real quantum systems that operate outside the lab, which is rare and extremely hard. So tell us, why is this project a high priority right now?
It's a high priority for several reasons. First of all, as many of you have, you want to speak in this thing? Test. Does that work better? Got it. It's a high priority for several reasons. One is, as many of you know, GPS is very vulnerable, subject to interference, subject to spoofing. We need an alternative, something that gives us timing and position even in absence of GPS signals. Furthermore, space itself is going to become a commercial arena. And what I would say about quantum technology in particular is it may seem exotic today. You heard Professor Du talk about laser cooling of atoms to near absolute zero. In the future, it's going to be absolutely routine. You'll become familiar with it as you are with the words megabit, gigabit, terabit. All the computer language that used to seem exotic is no longer exotic today. It's high priority for national security reasons, for commercial reasons. It's also high priority here because it's going to become the future and every day. And by the way, it's a great pleasure to be among the best engineering entities in the country and to be working here and develop a relationship between inflection and a very long-term relationship with the engineering and physics that's occurring here that will enable this quantum technology of the future.
Yeah, that's great. I can see the headlines already. You know, quantum is no longer just that buzzword that was thrown around all the time. It's the next generation way to make navigation and timing much more trustworthy, which is such an exciting future that lies ahead of us. Now I want to talk about why this team specifically can pull this off. Professor Baltaseva and Dr. Anderson, please feel free to chime in. What's special about the Purdue Inflection partnership? What do Purdue and Inflection bring to the table that makes this more than just a research idea?
I will let Dana to start because I want to paint a broader picture after this.
The first thing that I want to tell you is that quantum in space, quantum for navigation is just one aspect. In fact, with quantum technology, we can detect radio frequency signals in ways that we've never done before. We can put networks in space in ways that we've never been to before. We can do, for example, mineral exploration around the moon and asteroids with the help of quantum technology and monitor the Earth. With this breadth of engineering, technical challenges, and so on, it really means a breadth of backgrounds of contributing to the advances of engineering. And furthermore, you can do with the same kind of technology you tell time with, you can also do quantum computing, for example, enabling the kind of processing that we've never been able to do before. Now let me hand it over to you to broaden it out.
Thank you. Before I broaden it, I would like to mention, actually, as much as all of us are excited about this project, the idea of bringing quantum to space belongs to my dear colleague Vlad Shalev sitting here. And Arvin, that's because he got so excited after the first announcement. You know, he was bubbling. He said, you know, Purdue team is going to be in space. And so the next quantum meeting, it came up. So why not? This excitement, I think, what helped Vlad, together with Andy Weiner and Chris Green over a decade ago, actually to start the entire quantum effort. So I'm using the stage to actually promote the umbrella of quantum efforts here at Purdue. Purdue Quantum Center at that time later became Purdue Quantum Science and Engineering Institute, nowadays led by Professor Michael Manfra, and that actually unites efforts on this campus that is serving the sole purpose to join fundamental quantum science with engineering to push for real life applications. And I think this is in the heart of what Purdue and Inflection wants to do together. We are working with lead industrial partners as Inflection and trying to see how we leverage Purdue's strength in quantum materials, quantum photonics, machine learning, atomic optics, and many other areas to actually bring devices to real life. And in addition to this exciting Purdue One project that we already, we have itchy feet from our team and students and postdocs to start working on that with Dana and Shengwang. I wanted to mention that the partnership with Inflection actually goes beyond that. And one of the areas that is, as exciting as this one is actually the intersection or crossroads of quantum and AI and machine learning. And I just wanted to bring this up because, what's exciting is to ride with the wave of ongoing technology revolutions. And, space is one, quantum is another. But we can't ignore the big data, AI, and machine learning, which is now everywhere. So bringing machine learning to quantum solvers, to this neural atoms array that work with as quantum computers is another big area where we see a lot of exploration and advances coming up next. And that's another twist that Purdue and Inflection can work together on, bringing machine learning to actually enable better and more precise quantum sensors and communication systems.
Thank you. That was very beautifully put. I really loved that you said, why not, right? So much of the innovation that happens at the frontiers of human science and technology is because humans have dared to ask the question, why not, right? And I love that. I really loved hearing that. And I guess I'd love to wrap up this panel with one final question for you all. So this is, really just to tie back to the Purdue story, because today is about more than just the science. So we all know that Purdue is the cradle of astronauts, but Purdue One is also building the cradle of the next generation of engineers who will actually operate space systems like this. Many of us are in the audience, and I'd like to know, what is the impact on engineering students' involvement and workforce development? I would love to hear from all of you on this.
Well, I can start and just say that if you want to attract the student, you have to think big. Look at all the sci-fi or movies and books. It's space travel, time travel, it's AI and robots, and that's all Purdue. What else can we say? It all happening here. So bringing together space, quantum, AI, is what young people love. We have requests every single day coming from young people to join the research as soon as they hear these three magic words, because that's just beyond what they can imagine, and that's the future.
And certainly, in this project, we involve engineering graduate student and undergrad student. So they will be the one really build up the system and bring it to the spacecraft. Even so, the person will not go there, but they will design and integrate the system, for the entire project. And also this semester I'm teaching applied quantum computing, and I think many of my students also here say, for this exciting news, see how quantum can go to the space. So we certainly will involve students. Yeah.
And I have to say, especially as a representative industry, there's a huge need for well-trained engineers, everything. Whereas the word quantum comes in, we so much need what I refer to as classical engineers who are quantum familiar. So whether it's electrical engineering, packaging, mechanical engineering, what have you, certainly aerospace engineering, there's huge need for it. And it is very rare, in my perspective, to be able to enter an industry and immediately be on the forefront of technology development. And for me, when I try to remember being way back when, the idea that you could be on the cutting edge, the very edge of where the world is going, it's unbelievable to have that opportunity. And I think many of you have that opportunity, and certainly quantum is one of those forefronts that marks new technology arena and the frontier.
I have goosebumps just from listening to you three speak. Thank you so much. Please join me in thanking our panelists. Thank you for your time.
Thank you.
All right. So the core idea behind our next research project is that we're exploring what it takes to manufacture and validate electronics in microgravity. Specifically, how can we use the space environment to improve semiconductor processing, thin films, and additive manufacturing integrity? Purdue One gives us a rare opportunity to move this from theory into reality. So today, we're going to talk about the science, the hardware, and how this next experiment is laying the groundwork for an orbital industrial economy. Please join me in welcoming the people making our future in space slightly less science fiction. Professor A.J. Malshi, Distinguished Professor of Mechanical Engineering and Director of Purdue's Center for In-Space Manufacturing, the nation's first center dedicated to space manufacturing. Mike Molnar, Founding Director of the Advanced Manufacturing National Program Office, Manufacturing USA, at the National Institute of Standards and Technology, helping shape America's industrial strength. And finally, Dr. Jonathan Volk, Business Development Director for Voyager Technologies. His primary focus is leading in-space manufacturing and advanced materials research efforts on Starlab, the next-generation space station that Voyager is developing with its partners. Thank you for being here. So Mike, I want to start with you. You've led the charge for Manufacturing USA in strengthening domestic manufacturing in America. But why should the average person, or even the average tech CEO, care about advanced manufacturing in space? Do you think this is a matter of national security, economic edge, or purely scientific discovery?
Interesting question. Well, you know, the first panel, it was so exciting. You even said Star Trek, right? And it's exploration and it's science. And then you have a panel on manufacturing. That sounds, isn't that crass? No. I just my friend and colleague AJ just gave me a tour of the Purdue Materials and Manufacturing Lab. And I got to say, that personified this notion. So manufacturing is the ability to do something. It's to make something, right? And so this isn't a matter of crass commercialism. This is really how you build something. And I would just say, if you're not familiar with Manufacturing USA, it's still a new program. The institutes, these are mass collaboration where industry and academia work together. Well, the very first institute is called America Makes, on the topic of additive manufacturing. It's sponsored by the Department of Defense, and you wonder, why is that? Well, because one of the key needs that we have, if you are on an aircraft carrier way out in the Pacific and something breaks, do you have spare parts for everything that could break? Or is it a smarter idea to have ones and zeros and be able to 3D print what you need? Well, if that makes sense in the middle of the Pacific, doesn't it even make more sense in low Earth orbit? So that's the whole notion here of this experiment. It's the ability to make something. Now, microgravity, it is a very different environment, huge challenges, but it's also huge opportunities. You can make perfect spheres, right? Or so the deposition in 3D printing, what we think is very easy here is quite challenging in space. So in short, Manufacturing USA, the question, it is really the age-old matter of teams working together. Engineering is a contact sport, and this Purdue One with professors and students, they're really testing the boundaries of how do we get our hands around these sorts of questions to not only make things in low Earth orbit that you cannot easily make on Earth, but most importantly, as we go into a new era of space, a commercial space economy, we need to have the ability to repair and replace up there, way above the gravity well. And that's why I'm so excited that Purdue's leading this charge.
Thank you so much. I think this is the first time I've ever had someone so eloquently explain manufacturing to me, so thank you for that. I'm sure the audience appreciates it as well. But yes, Professor Malshi, we hear the next generation of space endeavors, Space 2.0, as it's called, for commerce and defense, in addition to the exploration phase of Space 1.0. In layperson's terms, how can manufacturing in space benefit humankind on Earth?
Well, that is an excellent question. Before I start, I really wanted to thank Dean Raman, you, Corina, where is Corina? She's somewhere, and your all team to make this possible. This is historic. We are truly making a history. And I would like to acknowledge my colleague Bill, Michael, Noah, Liz, Salil, Ethan. They're all going to be a part of this, and there are many others. What I would like to point out to you is that we talk cradle of astronaut. That is almost synonymous with name Purdue. But what is beyond cradle is what I'm asking a question. 2.0. When our countries like China, Russia, and all active in the space as a domain, America got to be active. We are about to retire International Space Station. If human has to go in space, has to habitat in space, information has to go with it. If information is going, electronics is going. If the electronics is going, chips are going, quantum is going. So this is all going in space. It is leaving Earth now. And it is not if, it is now. And that is very, very monumental at this point in time, and how Purdue is a very important part of that. Now, coming to your point, the second important part to manufacturing, which is almost the sister of manufacturing, is what called supply chain. Every time nation gets challenged with in excess of $1 trillion problem, which has happened 5 times from year 2000, the question is, well, manufacturing is challenged, but supply chain is a bigger problem. Look at critical materials, lithium, and all that. Now think about that we are building an economy in low Earth orbit, LEO. What is going to be our problem? To build a supply chain from Earth to space. Now that is shifting the gears, big time. You have Earth, LEO, MEO, all the way to the lunar. So you are building a supply chain 5 times plus than the Earth. Now what is going to be calling for manufacturing? On-demand manufacturing. How you manufacture on demand and not just manufacture and you wait for the customer. So think about tomorrow, just this weekend, TerraWave, Blue Origin just announced 4,000 new satellites. We already have few thousands already there. Then we have space stations coming from Voyager, Axiom, VAST, orbital reefs, and there could be more free flyers coming. You're going to have a whole civilization there now. What happens if something breaks down? Are we going to send something back to the Earth? Because escaping the gravity and coming back is very expensive. So we do need on-demand. And now put 2 dots together, on-demand manufacturing, and now electronics in space. So we will call ODME, on-demand electronics manufacturing. And this experiment that we are about to do has 2 parts. We always ask a question that what happens to physics in space? Fluids is one. Professor Kalikart is one of the world experts. Second, diffusion is another part. So for us to make electronics, repair electronics, rewrite the electronic packages, chips, we need ability to process, manufacture, print, on demand, on site at a given point when the customer asks you. And that's what this experiment is going to try. The second part of this, and which is very exciting, and I'm very happy to share, we are going to ask a question, and I will ask this question to all my colleagues here. Why semiconductor chips are always flat? Why? $1 trillion economy depends on 2 dimensions. Chips, flat. Why? This is a paradigm shift. So we are going to make a paradigm shift to make 3-dimensional chips in space. And so 2 experiments, part A, part B, are going to challenge what we do on Earth, but for on-demand electronics manufacturing. That's what Space 2.0. And I'm just super excited that many, many students are going to be a part of this, and I teach a class for in-space manufacturing. I thought first time maybe 10, 15 students would show up. I had capped 50 students, all boom, just like that. So that tells me that, AJ, get geared up. We are ready for taking the next flight, and here it is. Thank you.
Thank you so much for that amazing answer. You mentioned Voyager, and I'd like to go on to John. I'd like to talk about translating the science to systems. How will Starlab and other commercial platforms support in-space manufacturing in the near future, like those being demonstrated on the Purdue One mission? So, how can organizations like universities, national space agencies be able to make use of Starlab's capabilities?
First off, I can validate I was in AJ's class today. Did have about 50 people there. It was standing room only. The guest lecture was a little boring, but it turned out okay, I guess. But no, to answer your question, so Starlab, a commercial space station, we're very focused on in-space manufacturing. The Center for In-Space Manufacturing here at Purdue, we want them to be heavily involved and utilize Starlab's capabilities to support all the great work that's going on here. So maybe we'll call it, the next mission would be Purdue, well, I guess Purdue 3D for 3D chips or something like that. But anyway, what we see right now is it's great translating the science that's going to go on this Virgin Galactic mission to longer-term deployment on a commercial platform. Semiconductor manufacturing processes, obviously there's hundreds, thousands of steps, but if we can validate certain processes or certain steps in microgravity, that gives us great assurance that we're going to see great results when the full capability or a larger capability is going to get deployed on the Starlab, not just for a demonstration, but to actually make chips, to make products for terrestrial benefit. So obviously there's a lot of economics by it. But on Starlab, we're going to have traditional lab facilities like you see on ISS, but yet they'll be built this decade and not in the 1990s, or at least most of them. But we're also going to have a lot of space for users who want to just reserve space on Starlab. And a lot of these users, and they're not just commercial users, they're academic users, government users who want to reserve space for whatever they want to do, but especially for in-space manufacturing. So they can actually develop a business model, make product for a market on the ground. So it's a great opportunity to really, and it's a great platform to really show, hey, that there's a great need for in-space manufacturing, and we're going to have the ability to do that and for anyone to utilize it.
Thank you so much for that industry perspective. Mike, I'd like to ask you, what do you see as a few of the challenges for in-space production that organizations will have to address in order to fully realize this Made in Space title?
I don't know. And that's really the point. When you put something into production, when you go, it is one thing for some innovation in a Purdue lab, eureka, right? But then when you move it into low volume and then higher volume production, it's a different environment entirely. And you learn by doing. And so that's the point, is we all don't know until you try things. And this notion of Purdue One is trying things. I mean, the last panel about precision time, you think, well, it's just time, right? Well, I'm with NIST, day job, National Institute of Standards and Technology, and time.gov, we are pinged 16 billion times every day to synchronize time with the NIST master clocks, right? It sounds so easy. Well, at the precision level, at the quantum level, time is moving differently up there. NIST just published what the Mars standard time is, because time moves differently at different gravity periods. So when you think about that's just one thing, that time is moving differently, right? So when you talk about things happening at the advanced manufacturing scale, you won't know all the interplays until you try it, and then you're going to learn from it. So engineering is a contact sport. We're going to learn by doing, and the smartest people around, we can come up with a list of all the things we don't know, we do know, but I know that we're going to learn a whole lot more by giving it a try. And we're going to be doing something that is really testing the boundaries and studying the environment. One last plug, I mentioned NIST. One of the barriers and one of the enablers that this happens to manifest is standards. We will have a whole new era of standards that we don't even know of. So this is not just physical standards, but documentary standards, things that would, we need them to work flawlessly, repeatedly, reliably. Because if anything, space is an unforgiving environment. And if you have more and more people up there, you absolutely need, with certainty, what's going to happen, what happens when it fails, redundancies, and that's going to be an exciting new era. Sorry, I grew up with watching Star Trek. Space is the final frontier, and we don't know what we don't know, but the way to find out is giving it a try.
Thank you so much. Lastly, we are currently educating the future additions to the Cradle of Astronauts at Purdue, as I mentioned earlier. As we move towards an era of in-space assembly and manufacturing, what skills do you believe that today's engineering students need that maybe didn't exist 10 years ago? I'd love to hear from you all so we get the academic, government and industry perspective.
So I think what skills we need is exist at Purdue, because we call ourselves Boilermakers. And that maker skill is unfathomable and infinitely unlimited necessary. Because once you engage more than 2 human senses other than ears and eyes, touch, some things you don't want to smell, but if you happen to, you want to listen. But beyond, if you engage 5 senses in the art, skill, and the technology of making, you gather those skills. It is not about the degree only. Degree open the first door, skills open the second and the third and beyond. So the skill set of making, skill sets of thinking beyond what is taught in the textbook. Textbook is a book of history always. There are books to be yet written on the topics we are all talking here. Think about that for a second. Every textbook is a book of history. So we are no textbooks. So how do you learn without textbooks? AI is only good for the data we feed and happen to be a decent data. So biological intelligence and the artificial or synthetic intelligence integrate together for the art of making and the skill of doing that is limited, is required. And that is not exist in the textbook. You just got to engage 5 senses in that context board.
I'm going to answer this completely differently. Did I mention AJ just gave me a tour of the MML? And I was struck by these posters he made. People, process, product. And you know what? That is timeless. So when we talk about skills, I mean, when you train an electrical engineer and they get all of these skills, and arguably, they lose track of what's cutting edge a couple of years after graduation. Those are the tactical skills. I would argue the strategic skills is what Purdue is famous for, which is the fundamentals. And first and foremost, it's how to work together as a team and how to learn. So I'm going to be the contrarian here. I don't think we're going to have lots of new skills that we don't even know about. But the strategic skills that we will need in in-space manufacturing are the ones that have been the bread and butter of Purdue, which is how to work together as cross-functional, cross-disciplinary teams, how do we approach problems, and how do we learn how to learn.
I'll just say, as AJ mentioned, Space 2.0, it's becoming very, very commercial. Look no farther than up there, Purdue is working with Virgin Galactic, a commercial company, to do a suborbital flight. Commercial space stations are coming online. So with that being said, I think as undergraduate students, if you're in engineering, et cetera, with science, obviously those fundamental skills that you need to be a good engineer or scientist are paramount, but they also need to be complemented by business sense, because space is becoming more and more commercial. You might think of a great idea, but what's going to be the business sense? What is it going to sell to a company? So I think augmenting that, thinking about how can I incorporate understanding, how business works, et cetera, into my curriculum, into what I'm doing, I think is going to be very important to help make more well-rounded students going into the workforce who are great engineers, but also are very knowledgeable about how the space business and industry works.
I do want to actually make a comment about our MC. And one of the skills that you have as an engineer is a great communication. And why don't we all give a round of applause to our MC, which is done very few times, but I would like to do that. And I'm going to put you on spot. I did not tell you about this. But astro engineer given the great communication skill to tell a layman of what we do and how taxpayer, what they pay us, what consequential this is for the state, for the nation, and for their livelihood is one of the most important skills that as a manufacturing engineer I need to do. Otherwise, taxpayer would wonder what happened. How, is my kid is going to get better education? Am I going to live longer? Am I going to get better medicine? So ability to communicate as effectively as you have been is one of the most important skills, and I want to compliment you for that.
Thank you so much for that. I just want to say, my late grandfather would always say, your ideas are only as good as the way you communicate them.
That's right.
So you could have $1 million idea, but if you have no idea how to pitch it to somebody, you have no idea how to explain it in layperson's terms, it's worth nothing.
Beautiful.
So thank you for that compliment. I'm very flattered. Thank you. Ladies and gentlemen, please join me in thanking our final panelists for the evening. Thank you so much for your time. Before we wrap up, I'd like to offer a sincere thank you again to Dean Rahman, to our strategic partners at Virgin Galactic helping make Purdue One possible, and to every panelist who shared not just the exciting parts of this work, but the reality of what it takes to push this technology forward. In both panels tonight, the common thread I noticed is this: history isn't something we watch. It's something we're invited to participate in. Because you don't have to wait until you get your PhD or your first job to be part of work like this. Purdue One is a reminder that proximity to excellence changes what you believe is possible, and Purdue's greatest advantage has never been just the history, it's been the pipeline. Students who walk into labs, ask questions, slowly becoming the people who lead these missions. To make this personal for a moment, when I was a junior in high school, I remember applying to Purdue because I was inspired by the greats: Neil Armstrong, Gus Grissom, Sirisha Bandla, so many others. Purdue felt like the place to be where ordinary students could grow into extraordinary engineers. Now, as I prepare to graduate this semester, what I've learned is that Purdue's legacy isn't just a list of famous alumni. It's something you can tangibly feel in rooms like this, when a university puts students close enough to the frontier that history stops being just a chapter in the textbook and becomes something, as I mentioned earlier, you're invited to participate in. So to everyone listening, I want to leave you with one message. The future doesn't reward the most ready. It rewards the people who step forward anyway. To our team and experiments flying on Purdue One, we're proud of you. We're cheering you on, and we can't wait to see what your work unlocks. Godspeed, Purdue One. My name is Tendril Kamal, and it was, once again, my privilege to be your moderator tonight. Thank you all for being here this evening. Please join us for light refreshments at the reception immediately following this program. With that being said, boiler up and hail Purdue.